We have two particles with the spin half of unity which can imagine as a top toy in the form of a half sphere. Suppose these two particles are identically, that is, they have the same internal properties or quantum numbers. We want to put them in the same place, for example, inside the sphere. There is some fundamental principle of nature, which usually called the Pauli exclusion principle, stating that no two particles with the spin half of unity can share the same quantum state at the same time. In our demonstrative example, this means that we cannot put in the same place, inside the sphere, two identical half-sphere. However, we can do this if we flip vertically one of half-sphere. In this case, our state will not have the same internal properties or quantum numbers. They will differ in the direction of the spin, or, more accurate, the projection of the spin. One half-sphere will correspond to the spin up, while other will correspond to the spin down. If we take a different particle, it will not feel these particles and it can share place with any of these particles. This procedure is nothing as the construction of the proton and other subatomic particles from an elementary particles, which was proposed by Gell-Mann and Zweig in 1964. According to their idea, the proton, neutron and other similar particles with half-integer spin, called baryons, consist of three elementary particles. Particles with integer spin, called mesons, consist of two elementary particles. So, that problem was the following: think out an elementary particles with some internal properties, which can be used to construct all known particles. They introduced only three particles, which was called quarks by Gell-Mann, and constructed all known at that moment particles, not only baryons, but also mesons.